Okay, we are back and better than ever as usual, and we are talking about discrete probability distributions. And we talked briefly about that in the previous video. And the objective for this video is to recognize what is a probability distribution, to be able to make one, and also to prove that one is a probability distribution. All the probability distribution is showing all of the possible probabilities of an event, the probabilities of each outcome, I should say. Now, if we're talking about a particular event, each individual probability will be between 0 and 1 inclusive, and the sum of those probabilities from I equals 1 to the number of possible outcomes, little p stands for I, must equal to 1. In other words, each of the probabilities must add up to 1. And we can show this as a table, as a graph, or as a function. Don't get confused by this probability mass function. It's just a function, p of x. Okay, so we're just going to do a couple of examples here. A magazine store recorded the number of magazines purchased by its customers in 1 week. 23% of the customers purchased 1 magazine, 38 purchased 2, 21 purchased 3 magazines, 13% purchased 4, and 5% purchased 5. What is the random variable? Well, the random variable, x, is number of magazines purchased. That's easy. Okay, so clearly within that little story, it's the number of magazines purchased. And what are the possible number of magazines purchased? Based on this data, we're assuming that they've taken care of all of the customers in 1 week. In other words, every customer that walked in there either purchased 1 magazine, 2 magazines, 3 magazines, 4 magazines, or 5 magazines. Okay, and make a probability table for the random variable. Well, you just make a little table. That's no big deal. I'm just going to do this. Let's see, I'll do this. Okay, and little x represents all of the numbers. And let's see, 1, 2, 3, 4, and 5. And then we're going to do the probability of a random event equaling the individual. We use the individual one. If we have a bunch to choose from, we use a lowercase to represent all of the individual ones. Don't get confused with that. It's basically the same thing. It's just distinguishing. When we want to talk about all of them, we'll use a little x, and an individual one we'll use a cap X. The probability of a randomly selected customer during the week purchasing 1 magazine is easy. It's just 0.23. 2 magazine is 0.38. 3 magazines is 0.21. 4 magazines is 0.13. And 5 magazines is 0.05, matching up to the percentages. Okay. And then graphing it, well, that, whatever, that could be easy. Oh, they say a spike graph. Okay, fine. So probability, let's see, the greatest probability is 0.3. So I'll say that this is the probability axis, and this is, I don't know, mags purchased down here. Very simple. So our possibilities are 1, 2, 3, 4, and 5. And let's see, 0.1, 0.2, 0.3, 0.4 ought to do it. 0, 0.4, and I'll put 0.2 so it doesn't get crowded here. Our origin is here. So 1 magazine was what, about 0.23. And draw the stick, 0.38, maybe about here. Let's see, 0.21 right near the 2. I'm sorry, this is slanted. That's horrible. 0.13, maybe right here. And what's this, 0.05? This is point, so that's half of that, so that's about right here. I suppose it would be good if I labeled these 1, 2, 3, 4, 5. So just a quick sketch, and we've represented it with our probability distribution with a table and a graph. No big whoop. Okay. show that the following are probability distribution functions. In other words, show that p of x equals x squared plus 1 over 34. And my possible outcomes for x equal 1, 2, 3, and 4. So in order for this to be a probability distribution functions, we have to satisfy two different criteria. The first criteria is that 0 is less than or equal to p of x sub I is less than or equal to 1. In other words, the probability of each one of these must be between 0 and 1 inclusive. In other words, it could be 0 and or it could be 1 and anything in between. And then the second criteria is that the sum of each of those probabilities must equal 1. So that's all we have to show. So basically, we just have to replace x, each value of x, into this function and get each individual value. For example, if I say replace x with 1, I'm finding the probability that x is equal to 1 if it's a probability distribution function. If I replace x with 3, I'm finding the probability of a randomly selected event, whatever these represent, is 3. Could be 3 magazines like we had before. So what does that look like? Okay, well, if we do each one of those, probability of 1, 2 over 34, 2, 5 over 34, and on down the line, just getting our values there. Are they between 0 and 1? They certainly are. None of them is less than 0. None of them is greater than 1. And do they add up to 1? Yes, they do. If I add each one of those, they add up to 1. And lo and behold, we have proven that p of x is a probability distribution function. Same thing here, except I have my binomial expansion formula. So you can crank this on your calculator, obviously, is how you would do this one. Replacing x with each of the variables here. There's the main function, and here they all are worked out all the way to 3. I'm not going to work that out for you because it's just arithmetic. Maybe we go through, I don't know, this one. 3 choose 1 is 3. 0.6 to the first power is 0.6. 0.4 squared is 0.4 squared, that'd be 0.16. You add that up, it's 0.288. These are the probabilities. Each one of them is less than 1, so I've satisfied this criteria right here. I guess it'd be good if I had a pen, this criteria right here. And then do these add up to 1? They certainly do. If you add these up, they add up to 1. So we have proven it. All probabilities lie between 0 and 1, and the sum of the probabilities is 1. Therefore, both of these are probability distribution functions. They must satisfy both of those criteria. All right, that's it for this. We will see you next time. See ya!